The Arctic wind cuts through the frozen tarmac at Erland Air Station. It is minus 20 degrees Celsius. A lone F-35A Lightning II touches down on a runway glazed with ice. The pilot deploys the throttle to idle, but the jet keeps sliding forward. At this speed, on this surface, the brakes alone cannot stop 40,000 pounds of advanced stealth technology before it careens off the end of the runway. Then, in a fraction of a second, a small pod between the vertical stabilizers opens. A white parachute billows out behind the aircraft. The jet decelerates rapidly, coming to a controlled stop with meters to spare. That parachute, that seemingly simple piece of fabric, represents one of the most significant contributions any NATO partner nation has ever made to the world's most advanced fighter jet. And it was designed, tested, and perfected by Norwegian engineers who refused to accept that the F-35 could not operate in their unforgiving Arctic environment. Welcome to the story of how a small Scandinavian nation transformed NATO's fifth-generation fighter. If you find this history fascinating, subscribe to the channel and let me know in the comments where you are watching from today. The story begins not in the frozen fjords of Norway, but in the boardrooms of the Pentagon during the early 1990s. The Cold War had just ended, the Soviet Union had collapsed, and the United States military found itself with an aging fleet of fighter aircraft designed for a conflict that no longer existed. The F-16 Fighting Falcon, the workhorse of NATO air forces, was approaching 3 decades of service. The F-15 Eagle, America's premier air superiority fighter, was even older. Military planners understood that the next generation of threats would require a revolutionary approach to aerial combat. The concept that emerged was audacious. Instead of developing separate aircraft for the Air Force, Navy, and Marine Corps, the Department of Defense proposed a single airframe that could be adapted for all 3 services. The Joint Strike Fighter program, as it came to be known, promised unprecedented cost savings through commonality. 1 aircraft, 3 variants, thousands of jets for the United States and its allies. It sounded elegant on paper. In reality, it would become the most complex and expensive weapons program in human history. Lockheed Martin won the contract in 2001, beating out Boeing's competing design. The company's Skunk Works division, legendary for creating the U-2 spy plane and the SR-71 Blackbird, led the development effort. Their chief challenge was integrating stealth technology, which had previously been reserved for specialized aircraft like the F-117 Nighthawk, into a multi-role fighter that could also engage in close air support, strike missions, and dogfighting. The engineers in Palmdale, California worked around the clock. They shaped every surface, every edge, every inlet to deflect radar waves away from enemy receivers. They buried the engine deep within the fuselage. They designed internal weapons bays that could carry missiles and bombs without compromising the aircraft's radar signature. But Lockheed Martin was not working alone. From the very beginning, the F-35 program was designed as an international partnership. 8 nations joined the United States in funding the development phase: the United Kingdom, Italy, the Netherlands, Turkey, Canada, Denmark, Australia, and Norway. Each partner nation contributed financially and in return received the opportunity to compete for contracts to manufacture components for the aircraft. This was not charity. It was strategic calculation. The more nations invested in the F-35, the more committed they would be to purchasing and operating it, and the more aircraft produced, the lower the per-unit cost would become. Norway's participation began in 2001 when Oslo signed on as a Level 3 partner in the system development and demonstration phase. The investment was modest by American standards, but significant for a nation of just 5 million people. Norwegian officials understood that their aging fleet of F-16s would need replacement within 2 decades. They also recognized an opportunity. If Norwegian companies could secure manufacturing contracts for F-35 components, the economic benefits would extend far beyond the purchase of new fighter jets. The man who championed Norway's involvement was a career defense official named Bjørn Olaf Knudsen. He had spent years building relationships with American defense contractors and Pentagon procurement officers. He understood that Norway's value to the program was not just financial. It was geographical and operational. No other F-35 partner nation operated in conditions as extreme as the Norwegian Arctic, temperatures that plunged to 40 degrees below zero, runways covered in snow and ice for 6 months of the year, limited daylight during the polar winter. If the F-35 could be made to work in Norway, it could work anywhere. Knudsen made this argument repeatedly in meetings with Lockheed Martin executives. Norway, he insisted, was not just a customer. Norway was a testing ground. The first major Norwegian contribution to the F-35 program came not from a government laboratory, but from a defense company headquartered in the town of Kongsberg, about 80 kilometers southwest of Oslo. Kongsberg Gruppen had been manufacturing weapons for more than 2 centuries. Founded in 1714 to produce muskets for the Danish-Norwegian army, the company had evolved over the generations into a sophisticated defense contractor specializing in missiles, remote weapon systems, and naval strike technology. By the early 2000s, Kongsberg's engineers were working on a project that would become synonymous with Norwegian innovation in military aviation: the Joint Strike Missile. The challenge they faced was formidable. Traditional anti-ship missiles were large, heavy, and required external mounting on aircraft. This external carriage created drag and, more critically, reflected radar waves that announced the aircraft's presence to enemy air defenses. If the F-35 was to maintain its stealth advantage while carrying a ship-killing missile, that missile would need to fit inside the aircraft's internal weapons bays. No existing missile met this requirement. So Kongsberg's engineers designed one from scratch. The Joint Strike Missile, designated NSM for the air-launched variant, was a masterpiece of miniaturization. At 4 meters in length and 400 kilograms in weight, it was compact enough to fit inside the F-35's internal bay, while still carrying a 125-kilogram warhead, capable of destroying a warship. Its range exceeded 500 kilometers, allowing the launching aircraft to remain far outside the envelope of enemy air defenses. But the missile's most innovative feature was its guidance system. Unlike earlier anti-ship missiles that relied on active radar seekers, which could be detected and jammed by enemy electronic warfare systems, the Joint Strike Missile used an imaging infrared seeker combined with an autonomous target recognition algorithm. In simple terms, the missile could see its target and distinguish between a warship and a civilian vessel without any guidance from the launching aircraft. The development process took more than a decade. Kongsberg's engineers conducted thousands of simulations. They tested the missile's seeker against every type of ship in NATO's registry. They worked with Lockheed Martin to ensure perfect integration with the F-35's weapons management system. They flew prototype missiles from the Norwegian coast, tracking their performance against target vessels in the North Sea. Each test revealed problems. The seekers struggled to distinguish targets in heavy sea clutter. The missile's flight profile generated more heat than anticipated, risking detection by enemy infrared sensors. The data link that allowed the missile to receive mid-course updates from the launching aircraft proved vulnerable to jamming. One by one, the Kongsberg team solved these problems. They rewrote the target recognition algorithms. They redesigned the missile's thermal signature. They hardened the data link against electronic interference. By 2018, the Joint Strike Missile was ready for operational deployment. It was the first missile in the world specifically designed for internal carriage on the F-35. And it gave Norway a strategic capability that few nations possess, the ability to strike enemy warships from hundreds of kilometers away without ever being detected. But the Joint Strike Missile was not Norway's only contribution to the F-35 program. There was another problem that Lockheed Martin's engineers in Texas had never fully solved. A problem unique to the Arctic environment where Norway operates, the problem of stopping. The F-35A, the conventional takeoff and landing variant operated by the Norwegian Air Force, was designed primarily for operations from long, well-maintained runways in temperate climates. Its braking system was adequate for such conditions, but Norwegian runways are neither long nor temperate. The main operating base at Ørland has a runway of just under 3,000 meters. In summer, this is sufficient. In winter, when that runway is covered in a layer of ice, it might as well be a hockey rink. The friction coefficient of ice is so low that traditional brakes become nearly useless. An aircraft landing at 200 knots would simply slide off the end of the runway into the snow. Norwegian pilots had dealt with this problem for decades with their F-16s, which were equipped with drag chutes. These parachutes, deployed immediately after touchdown, created enormous aerodynamic drag that helped slow the aircraft regardless of runway conditions. When Norway selected the F-35 as the replacement for its F-16 fleet in 2008, officials immediately raised the issue of winter operations. Without a drag chute, they argued, the F-35 would be grounded for months during the Arctic winter. This was unacceptable for a nation that shares a 198-kilometer border with Russia. Lockheed Martin's initial response was skeptical. Adding a drag chute to the F-35 would require modifying the aircraft's carefully designed stealth profile. Any external addition, however small, could increase the radar cross-section and compromise the jet's primary advantage. The engineers in Fort Worth calculated drag coefficients, radar reflectivity, and weight penalties. They concluded that a conventional drag chute system could not be integrated without unacceptable trade-offs. The Norwegian engineers disagreed. Working with their counterparts at Lockheed Martin, they proposed an innovative solution. Instead of a traditional drag chute, pod, mounted beneath the fuselage, they designed a small aerodynamic housing positioned on the upper surface of the aircraft, between the canted vertical stabilizers. This location had been chosen carefully. The stealth characteristics of the F-35 rely on shaping the aircraft to deflect radar waves away from their source. The area between the vertical stabilizers was already in the radar shadow of the aircraft's structure. A properly designed pod in this location would have minimal impact on the overall radar cross-section. The engineering challenge was immense. The pod had to be strong enough to withstand the forces generated when the chute deployed at high speed, yet light enough not to affect the aircraft's performance. It had to be sealed against the extreme cold of Arctic operations, yet easy to access for maintenance. It had to deploy reliably in conditions ranging from clear summer days to blinding winter blizzards. And it had to be designed so that it could be installed or removed with minimal time and effort, allowing the same aircraft to operate with or without the system, depending on conditions. The development program took 6 years. Norwegian and American engineers worked side by side, testing prototype pods in wind tunnels, on test rigs, and eventually on actual aircraft. The first successful deployment occurred in 2018, when a Norwegian F-35A landed at Ørland and deployed its drag chute for the first time. The parachute billowed perfectly. The aircraft slowed rapidly. The system worked. Today, the Norwegian drag chute system has been adopted by 4 NATO nations. Belgium, Denmark, and the Netherlands, all of which operate in similar winter conditions, have integrated the system into their F-35 fleets. Each installation represents a small but meaningful victory for Norwegian engineering, a demonstration that a nation of 5 million people can contribute innovations that improve the world's most advanced fighter jet. If you are enjoying this deep dive into military aviation history, take a moment to hit the subscribe button. Your support helps us continue producing content like this. The story of Norway's F-35 program is also the story of a small nation punching above its weight in the global defense industry. When the F-35 program began, American officials assumed that most components would be manufactured in the United States. Partner nations would contribute financially, but the industrial benefits would remain largely domestic. Norwegian officials pushed back against this assumption. They negotiated aggressively for Norwegian companies to compete for component contracts. They argued that spreading manufacturing across partner nations would reduce costs, diversify supply chains, and strengthen political support for the program. The results exceeded expectations. Norwegian companies today manufacture components for every F-35 produced anywhere in the world. Kongsberg produces not only the Joint Strike Missile, but also composite structural components for the airframe. Nammo, another Norwegian defense company, manufactures the 25mm ammunition used by the F-35's internal gun. Kitron produces electronic assemblies. GKN Aerospace Norway manufactures tail sections and horizontal stabilizers. In total, Norwegian industry has secured contracts worth billions of dollars, creating thousands of high-skilled jobs in a country where defense manufacturing had been a minor sector just a generation ago. This industrial participation has strategic as well as economic significance. Because Norwegian companies manufacture components that are integrated into every F-35, Norway has a stake in the program's success that goes beyond its own fleet of 52 aircraft. Norwegian workers, Norwegian engineers, and Norwegian executives are embedded in the global supply chain. Their knowledge, their skills, and their relationships give Norway influence in the F-35 program that far exceeds what its financial contribution alone would justify. The first Norwegian F-35 took flight in 2015 at Lockheed Martin's facility in Fort Worth, Texas. It was a moment of national pride, broadcast on Norwegian television and celebrated in the country's newspapers. The aircraft, designated AM-1, wore the distinctive red, white, and blue roundel of the Royal Norwegian Air Force. Its pilot, a Norwegian officer who had trained for months in American simulators and training aircraft, reported that the jet handled beautifully. The stealth technology that had been so carefully designed into every surface made the F-35 nearly invisible to radar. The advanced sensors gave the pilot unprecedented awareness of the battle space. The fly-by-wire controls made the aircraft responsive and forgiving. Over the following years, additional aircraft arrived in Norway. Each delivery was an event. Crowds gathered at Ørland to watch the jets land. Politicians gave speeches. Veterans of the F-16 era, who had flown those aircraft through countless exercises and occasional real-world intercepts, welcomed the new generation of pilots who would carry on their mission. By 2019, the Royal Norwegian Air Force declared initial operational capability with the F-35. This milestone meant that Norwegian pilots and maintenance crews had demonstrated the ability to fly and sustain the aircraft in combat conditions. It was not a symbolic achievement. It reflected years of intensive training, infrastructure development, and organizational adaptation. The transition from F-16 to F-35 required changes at every level of the Norwegian Air Force. The F-16 was a relatively simple aircraft by modern standards. A skilled mechanic could diagnose and repair most problems with basic tools and training. The F-35 is orders of magnitude more complex. Its integrated avionics suite generates more data in a single flight than an F-16 generates in a year. Its stealth coatings require specialized maintenance in climate-controlled facilities. Its software must be updated regularly to address bugs, add capabilities, and respond to evolving threats. The mechanics who once worked on F-16s had to be completely retrained. Many were sent to the United States for courses at Lockheed Martin facilities. Others attended specialized programs developed jointly by Norwegian and American instructors. The pilots faced an equally steep learning curve. Flying the F-35 is fundamentally different from flying the F-16. The older aircraft required the pilot to interpret data from multiple sources and integrate that information mentally to build a picture of the battle space. The F-35 does much of this integration automatically. Its sensors, including the APG-81 Active Electronically Scanned Array Radar, the Electro-Optical Targeting System, and the Distributed Aperture System that provides spherical awareness around the aircraft, feed data to a central computer that fuses the information into a coherent display. The pilot no longer scans multiple screens and instruments. Instead, the pilot receives a single, unified picture of everything the aircraft knows. This capability is revolutionary. In earlier generations of fighter aircraft, the pilot with the best situational awareness usually won the engagement. Situational awareness depended on training, experience, and the ability to process multiple information streams simultaneously under the stress of combat. These skills took years to develop. Many pilots never fully mastered them. The F-35 levels this playing field. Even a relatively inexperienced pilot, with the help of the aircraft's integrated systems, can achieve situational awareness that would have been impossible for the most skilled aviators of previous generations. But the F-35's most important capability is not any single sensor or system. It is the ability to share information with other aircraft and platforms in real time. The Multifunction Advanced Data Link, or MADL, allows F-35s to communicate with each other using a highly secure, low probability of intercept transmission. This means that a flight of 4 F-35s does not operate as 4 individual aircraft. It operates as a single networked system, with each pilot seeing everything that any aircraft in the flight can see. If one F-35 detects an enemy aircraft, all 4 pilots see that detection immediately. If one F-35 is locked onto by an enemy missile, all 4 aircraft know instantly. This networking extends beyond F-35s. The aircraft can share data with other NATO assets, including AWACS aircraft, ground-based air defense systems, and even naval vessels equipped with compatible data links. In theory, an F-35 operating over the Arctic could provide targeting data to a destroyer in the Norwegian Sea, enabling that ship to launch missiles at targets the F-35 has identified but cannot engage itself. This level of integration represents a fundamental shift in how air power is employed. The F-35 is not just a fighter, it is a node in a vast network of sensors and weapons that can be coordinated across thousands of kilometers. Norway's geographic position makes these networking capabilities particularly valuable. The country's northern regions lie at the edge of NATO territory, facing Russia across the Barents Sea and the Arctic Ocean. During the Cold War, this border was one of the most heavily watched in the world. Soviet bombers flying from bases on the Kola Peninsula would probe Norwegian airspace regularly. Norwegian F-16s, guided by radar stations scattered along the coast, would scramble to intercept. It was a deadly serious game of cat and mouse, played out in the darkness of the polar winter. After the Soviet Union collapsed, tensions eased. The intercepts became less frequent. Norwegian defense budgets shrank. Some questioned whether the threat from the north had disappeared forever. Then, in 2014, Russia annexed Crimea. The comfortable assumptions of the post-Cold War era shattered overnight. Suddenly, the border with Russia looked dangerous again. Russian military activity increased. Long-range bombers resumed their Cold War-era patrols. Submarines, which had been rusting at their piers for 2 decades, put to sea again. The Arctic, which had seemed like a frozen backwater, became a theater of strategic competition. Norway's response was to accelerate its military modernization. The F-35 program, which had been proceeding at a measured pace, became a priority. Additional funding was allocated. Timelines were compressed. The goal was clear. Norway needed fifth-generation fighters in service as quickly as possible to deter Russian aggression and demonstrate NATO's commitment to defending its northern flank. The Russian threat is not theoretical. Norwegian F-35s have conducted real-world intercepts of Russian aircraft approaching NATO airspace. In February 2025, Norwegian jets shadowed Russian bombers near the Arctic, demonstrating that the new aircraft were fully combat-capable and ready to defend Norwegian sovereignty. These intercepts are carefully choreographed. The Russian aircraft fly along established corridors, probing NATO defenses, but not actually violating airspace. Norwegian jets rise to meet them, flying alongside at close range, photographing the Russian crews and escorting them until they turn back toward Russian territory. These encounters are tense but rarely hostile. Both sides understand the rules. The Russians are testing NATO's response times and gathering intelligence on aircraft capabilities. The Norwegians are demonstrating vigilance and professionalism. Neither side wants an actual conflict. But the potential for miscalculation always exists. A mechanical failure, a misunderstood radio transmission, an impulsive decision by a young pilot. The history of aviation is filled with incidents that escalated from minor provocations to major crises. Every intercept carries this risk. The F-35's capabilities reduce this risk in important ways. Its sensors can detect Russian aircraft at much greater ranges than the F-16 could. This gives Norwegian pilots more time to plan their intercepts and reduces the likelihood of sudden, unexpected encounters. The aircraft's data links allow pilots to stay in constant communication with ground controllers, reducing the chance of misunderstandings. And the F-35's stealth makes it possible to observe Russian activity without being observed in return, gathering intelligence while minimizing the risk of provocation. But the F-35's most important contribution to deterrence may be its strike capability. Armed with the Joint Strike Missile, Norwegian jets can threaten Russian ships and installations at ranges exceeding 500 kilometers. This gives Norway a credible offensive capability that did not exist with the F-16. Russian military planners know that any conflict in the Arctic would expose their forces to attack from Norwegian aircraft operating from secure bases deep within NATO territory. This knowledge, the understanding that aggression would carry significant costs, is the essence of deterrence. The completion of Norway's F-35 fleet came in April 2025, when the final 2 aircraft were delivered to the Royal Norwegian Air Force. Norway thus became the first F-35 partner nation to fulfill its program of record, a distinction that reflects both the country's commitment to the program and the efficiency with which it managed the transition from F-16 to F-35. The delivery ceremony was attended by senior officials from Norway and the United States. Chauncey McIntosh, Lockheed Martin's vice president for the F-35 program, praised the partnership between the two nations. He noted that the relationship extended back more than 50 years to the days when Norway operated F-104 starfighters purchased from American manufacturers. The F-35, he said, would ensure that Norway remained at the forefront of military aviation for decades to come. Norwegian officials used the occasion to highlight their country's contributions to the program: the Joint Strike Missile, the drag chute system, the components manufactured by Norwegian companies and integrated into F-35s around the world. These achievements, they argued, demonstrated that small nations could be meaningful partners in major defense programs. Norway had not simply purchased American aircraft. Norway had helped make those aircraft better. Before we continue with the operational story, take a moment to like this video if you are finding value in it. Your engagement helps more people discover these stories of engineering and military history. The infrastructure required to support 52 F-35s is substantial. Norway has invested billions of kroner in upgrading its air bases to accommodate the new aircraft. Ørland, the main operating base in central Norway, received new hangars, maintenance facilities, and a hardened shelter complex capable of protecting aircraft from attack. The runway was reinforced to handle the F-35's weight. Fuel storage was expanded. Communication systems were upgraded. The base was transformed from a Cold War-era facility into a modern installation capable of supporting fifth-generation operations. But perhaps the most dramatic infrastructure development occurred far to the north, at Bardufoss Air Station. This base, located inside the Arctic Circle, had been constructed during the Cold War to provide forward operating capability for Norwegian fighters. Its unique feature was a complex of hangars carved directly into the mountain, providing protection against Soviet attack. After the Cold War ended, Bardufoss was placed in caretaker status. The hangars stood empty. The runways were maintained but rarely used. In 2024, Norway announced that Bardufoss would be reactivated to support F-35 operations. The mountain hangars were upgraded with modern climate control systems capable of maintaining the precise temperature and humidity required for F-35 maintenance. New facilities were constructed for the specialized materials used in stealth coating repair. Communications links were installed to connect the remote base with NATO's integrated air defense network. Bardufoss became, once again, a forward operating base for fighters defending Norway's Arctic frontier. The choice to reactivate Bardufoss reflected a broader strategic calculation. During the Cold War, Norwegian defense planning assumed that any Soviet attack would come quickly and with overwhelming force. Norwegian forces, including air forces, would need to disperse to survive the initial onslaught and then continue fighting from multiple locations. This dispersal strategy required bases throughout the country, including in the far north. After the Cold War, this strategy seemed unnecessary. The Russian military, which had inherited the Soviet arsenal, was in disarray. Its aircraft were grounded for lack of fuel. Its ships rusted at their piers. The idea that Russia could mount a coordinated attack on Norway seemed almost laughable. Norwegian defense planning shifted to focus on expeditionary operations, deploying forces abroad in support of NATO missions in the Balkans, Afghanistan, and Libya. The events of 2014 reversed this trend. Russia's annexation of Crimea and intervention in eastern Ukraine demonstrated that Moscow was willing to use military force to achieve its objectives. Subsequent exercises in the Arctic showed that Russian capabilities had been substantially restored. Norwegian planners recognized that the dispersal strategy of the Cold War era was once again relevant. If conflict came, Norwegian F-35s would need to operate from multiple locations, including Bardufoss, to avoid being destroyed in a single attack. The F-35's design facilitates this dispersed operations concept in ways that the F-16 could not. The older aircraft required substantial ground support equipment and large maintenance crews to sustain operations. Moving an F-16 squadron to a new base was a major logistical undertaking. The F-35, while more complex in some respects, incorporates design features that reduce its expeditionary footprint. Its engines are designed for easier removal and replacement. Its diagnostic systems can identify problems quickly, reducing the need for extensive troubleshooting. Its supply chain management system tracks parts automatically, ensuring that the right components are available at the right locations. Norwegian exercise programs have validated this dispersed operations capability. F-35s have operated from highways, landing on public roads that were temporarily closed to traffic and converted into improvised runways. In 2023, Norwegian jets demonstrated this capability for the first time, touching down on a highway and then taking off again after rapid refueling and rearming. The exercise proved that Norwegian F-35s could continue flying even if their main bases were destroyed or disabled. This highway landing capability had been demonstrated with F-16s as well. But the F-35 brings additional challenges. Its stealth coatings are more sensitive to debris damage. Its systems are more complex and require more careful post-flight inspection. The Norwegian Air Force developed specialized procedures for highway operations, training ground crews to prepare improvised surfaces and inspect aircraft quickly. These procedures, like the drag chute system, represent Norwegian adaptations of the F-35 to local conditions. The Joint Strike Missile remains the centerpiece of Norway's offensive capability. By 2025, the weapon had been fully integrated with the Norwegian F-35 fleet, giving pilots a standoff strike option that could engage targets hundreds of kilometers away. The missile's characteristics, its stealth, its autonomous guidance, and its ability to fit inside the F-35's internal weapons bays made it uniquely suited for operations in heavily defended environments. Kongsberg continues to develop the Joint Strike Missile, adding new capabilities and extending its range. Recent upgrades have improved the weapon's ability to operate in GPS-denied environments, where enemy jamming might prevent satellite navigation. The missile can now navigate using terrain contour matching, comparing the features it sees below to a stored digital map. This backup navigation mode ensures that the weapon can reach its target even if GPS signals are unavailable. Other nations have taken notice. The United States Navy has selected a variant of the Joint Strike Missile, designated the Naval Strike Missile, for its littoral combat ships and frigates. Australia has expressed interest in the weapon for its own defense forces. Japan has purchased the missile for its F-35 fleet. Each sale represents a validation of Norwegian engineering and a commercial success for Kongsberg. The company that once made muskets for the Danish Army is now a leading supplier of advanced weapons to the world's most sophisticated militaries. The relationship between Norway and the F-35 program illustrates how international partnerships can benefit all participants. The United States gained a capable ally in the Arctic, a region of growing strategic importance. Lockheed Martin gained innovations like the drag chute system that improved the aircraft's capabilities. Norway gained access to fifth-generation technology that would have been impossible to develop independently, along with industrial benefits that have transformed its defense sector. This model of partnership has influenced how other nations approach the F-35 program. Countries considering the aircraft look at Norway's experience and see a roadmap for maximizing the benefits of participation. They see that aggressive negotiation for industrial contracts can yield substantial returns. They see that unique operational requirements can be accommodated through collaborative engineering. They see that small nations can have meaningful influence on major defense programs if they engage actively rather than passively. The future of Norwegian air power will be shaped by the F-35 for decades to come. The aircraft has a projected service life extending past 2050. Norwegian pilots being trained today will fly these jets throughout their careers. The infrastructure investments being made now will support operations for a generation. The industrial relationships being developed will continue to generate contracts and create jobs long after the current program is completed. But the F-35 is not without challenges. The aircraft's complexity creates maintenance burdens that strain even well-funded air forces. Parts shortages have affected availability rates across the global fleet. Software updates, delivered regularly to address bugs and add capabilities, sometimes introduce new problems. The cost of operating F-35s is higher than for the F-16s they replaced, requiring ongoing budget commitments that compete with other defense priorities. Norwegian officials acknowledge these challenges while expressing confidence in the program's long-term viability. They note that many of the early problems have been resolved through software updates and supply chain improvements. They point to increasing availability rates as evidence that the aircraft is maturing. They argue that the capability advantages the F-35 provides justify the higher operating costs. And they emphasize that Norway's industrial participation helps offset those costs by generating revenues for Norwegian companies. The geopolitical environment that drove Norway's F-35 acquisition has only intensified since the program began. Russia's war in Ukraine, which began in 2014 and escalated dramatically in 2022, has demonstrated that large-scale conventional conflict remains possible in Europe. Russian nuclear exercises have reminded NATO members that deterrence requires credible conventional and nuclear capabilities. The Arctic, warming rapidly due to climate change, has become a new theater of competition as melting ice opens shipping routes and exposes resources that were previously inaccessible. In this environment, Norway's F-35 fleet provides capabilities that go beyond air defense. The aircraft serve as intelligence collectors, using their sensors to monitor Russian activity across the high north. They serve as communication nodes, linking disparate elements of NATO's defense network. They serve as symbols of alliance solidarity, demonstrating that an attack on Norway would engage the full weight of American military technology and the political commitment of the Atlantic Alliance. The 52 F-35s now in Norwegian service represent the largest fleet operated by any Nordic nation. Finland, which ordered 64 F-35s in 2021, will eventually surpass Norway in numbers. But Norway's head start, its operational experience, and its industrial contributions give it a leadership position in the region. Norwegian pilots train Finnish counterparts. Norwegian companies compete for Finnish contracts. Norwegian tactics and procedures inform Finnish doctrine. The community of F-35 operators in the high north is growing, bound together by common equipment and shared interests. This community extends across the Atlantic. Norwegian F-35s have participated in exercises with American forces, including joint operations with B-52 bombers in the 2024 Apex Buccaneer drills. These exercises test interoperability, the ability of different nations' forces to operate together seamlessly. They reveal problems with communication systems, command procedures, and tactical assumptions. They build relationships between pilots and commanders who might someday fight together in a real conflict. The human element of the F-35 story is often overlooked in discussions of technology and capability. But the aircraft are flown by men and women who have dedicated their lives to military service. Norwegian F-35 pilots come from a small, highly selective community. They undergo years of training before qualifying on the aircraft. They fly demanding missions in harsh conditions, often in darkness, often alone over the Arctic wilderness. They accept risks that most civilians never consider. The ground crews who maintain the F-35s work equally hard in conditions that are equally challenging. Erland and Bardufoss are not comfortable postings. The winters are long and dark. The weather is brutal. The work is demanding and technically complex. Yet the personnel who serve at these bases take pride in their role. They understand that they are maintaining aircraft that matter, aircraft that deter aggression and protect their nation. The engineers at Kongsberg and other Norwegian companies bring their own form of dedication. They have spent decades developing systems that push the boundaries of what is possible. They have solved problems that the world's largest defense contractors could not solve. They have earned respect that in an industry dominated by American and European giants. Their work continues as they develop new weapons, new systems, and new capabilities for the next generation of conflicts. Thank you for watching this exploration of Norwegian contributions to the F-35 program. If this content resonated with you, subscribe to the channel and share it with others who appreciate military history. Your support makes these deep dives possible. The legacy of Norway's F-35 program will be written over the coming decades as the aircraft prove themselves in exercises, intercepts, and perhaps someday in combat. The Joint Strike Missile will be launched in anger at some point against some target. in some conflict that no one can predict today. The drag chute will deploy on icy runways across NATO. The components manufactured by Norwegian workers will fly in F-35's from Japan to Israel, from the United Kingdom to Australia. And the example of a small nation making outsized contributions to a massive international program will inspire other countries considering similar partnerships. The story of the F-35 is still being written. New variants are in development, new capabilities are being integrated, new operators are joining the program. But the Norwegian chapter of that story is already significant. It demonstrates that geography need not be destiny, that a nation at the edge of the Arctic can compete at the highest levels of aerospace technology. It demonstrates that innovation can come from unexpected places, that the solution to a problem that stumped American engineers might emerge from a small town in Norway. And it demonstrates that military partnerships, properly structured and energetically pursued, can benefit all participants. The F-35 flying today over the Norwegian Arctic is not simply an American aircraft with Norwegian markings. It is a joint creation shaped by Norwegian requirements, improved by Norwegian innovations, and sustained by Norwegian industry. When that jet deploys its drag chute on an icy runway or launches a Joint Strike Missile at a distant target, it carries with it the knowledge and dedication of thousands of Norwegian engineers, technicians, and military personnel. Their contribution to the world's most advanced fighter jet will be remembered long after the specific details of development contracts and delivery schedules have been forgotten. The Arctic wind still howls across Ørland Air Station. The runways still freeze in winter. The long polar night still descends each December, plunging northern Norway into months of darkness. But in the hangars, illuminated by artificial light, the F-35's stand ready, their drag chutes are loaded. Their missiles are armed, their pilots are trained. And when the call comes, when Russian bombers appear on radar screens or threats emerge over the horizon, Norwegian jets will scramble into the darkness to defend their nation and their alliance. That readiness, built over decades of development and maintained by constant effort, is the true legacy of Norway's contribution to the F-35 program. It is a legacy of engineering excellence, strategic foresight, and unwavering commitment to collective defense. And it is a legacy that will shape the future of air power in the high north for generations to come.